Today's lecture is dedicated to quotient topology and the construction of real projective space. Okay, so let's get started with the concepts of quotient topology. So the story begins with the concept of equivalence relation on a set that we are all familiar with. So we have a set S, and we declare an equivalence relation on this set S, okay, which is reflexive, symmetric, and transitive. Okay. So once we define the equivalence relation, all the elements which are equivalent to each other, they form a class, and we denote such equivalence classes with this notation. Okay. So this is the equivalence class containing X in S. Okay. So all the elements in this class are equivalent to each other by means of this equivalence relation. Okay. So we denote the equivalence relation by twiddle. So if we have two elements X and Y belonging to this class, then X is equivalent to Y. Okay. All right. So an equivalence relation on this set partitions this set into disjoint equivalence classes. Okay. And so once you declare this equivalence relation on S, it partitions S into disjoint equivalence classes. Okay. So now you can form a set called S quotiented out by twiddle, by which we mean that S is quotiented out by this equivalence relation is a set whose elements are these equivalence classes. Okay. Okay, so there is a natural projection map which projects the starting set S to this set. Okay, this set has a name which is called the quotient set. Okay, or the quotient of S. All right. Okay, so there is this natural projection map under which X gets mapped to the class to which this X belongs. Okay. Okay. So it is immediate from this discussion that pi is surjective, but it is not necessarily injective. Okay. So there is an important remark on this notation. Ideally, we would denote by this a point in this quotient space, or quotient set to be more precise in this. So in this context, so far we have considered S as just a set. So it's a quotient set. So this class will be a point in this quotient set. All right. And by abuse of notation, with this same notation, we will describe a set in S, okay, that get projected to this point under this projection map. All right. So this also denotes a set in S whose elements are all equivalent to each other under the given equivalence relation. Okay. Good. So it depends on the context on which we are referring this as a class, as a set, or as a point. All right. Okay, so now let's assume that the set that we were discussing earlier is not just a set, but not just a set, it is also a topological space. Okay. So assume that S is a topological space. So now we want to describe an equivalence relation twiddle on this topological space S. Okay. Define twiddle on S. Okay. So now so once we do that, we are interested in giving a topology to this quotient set, okay, so that it becomes a topological space. So we define a topology on this quotient set by declaring that a set here would be an open set if and only if its inverse image is open in S. Okay, so let me write it for you here. U is open in this quotient set if and only if the inverse image of U is found to be open in S. And it makes sense to talk about this guy being open in S since S is a topological space. Okay, so it's immediate from the discussion that the inverse image of null set. Okay, so null set is an element here, and its inverse image is null set, and since null set is open in S, null set in S modded out by twiddle is also open. Okay. All right. So also we see that the total space S quotiented out by twiddle is open because by the surjectivity of the projection map, okay, we see that S quotiented out by twiddle, the inverse image of S quotiented out by twiddle is the whole topological space S, and since S is open in S, S quotiented out by 2 is open in the topology that we are discussing. Okay. So we have verified these two extremes in the definition of topology. Um, now let's assume an arbitrary collection of open sets in S quotiented out by 2. Okay. Right. So the point is that each of these sets, okay, is open in S. Okay. Right. And this is why this is so. It follows from the definition of quotient topology. Okay. So these are open sets in this so-called quotient space, and so the inverse image of these open sets under pi is taken to be open in S. Okay. For a given alpha. Okay. Now observe that since so each of such sets is open in S. So an arbitrary collection of open sets. So the union of arbitrary collection of open sets is open according to the definition of topology. So the arbitrary union of these open sets is open. Okay. In S. All right. But since we know that this guy is the same as the inverse image of the union of all these open sets U alpha, okay, U alpha here, then we immediately see that since this is open in S, this guy is also open in S. Right. And from the definition of quotient topology, then, this guy has to be open in S modded out by 2. Or so we have found that if you have an arbitrary collection of open sets in S quotiented out by 2, then their union is also open. Okay. All right. So now see that. So if you have a finite collection of open sets in S quotiented out by 2, one finds that the finite intersection of this collection is again open. This guy is open in S quotiented out by 2. Right? How do we find it? So this is something that we can see from here, because since each of this guy is an open set in this quotient space, therefore therefore the inverse image of these open sets is open, right? Is open in S, is open in S. So finite intersection of such open sets is again open in S, okay, since S is a topological space. So we have seen that this is open, right? And this is nothing but, from elementary set theory, we know that this is nothing but the inverse image of this finite intersection, right? So this guy is open in S, right? Now from the definition of quotient topology, this has to be open in S modded out by this twiddle. Right? So we started with the fact that this is a finite collection of open sets in S modded out by twiddle, and we ended up showing that their finite intersection is also open in S modded out by twiddle, which proves that under the definition we have provided earlier, S modded by twiddle is a topological space, correct? So the topology that we defined earlier is called the quotient topology on this quotient space. This is called the quotient space or a quotient topological space. So now we are going to discuss continuity of a map on a quotient. All right. So continuity of a map on a quotient. Okay. So we start with an equivalence relation denoted by twiddle. That twiddle be an equivalence relation on the topological space S, and give S modded out by twiddle the quotient topology. Okay. Suppose f be a continuous function from this topological S to some other topological space Y. Okay, we want this guy to be continuous. We also assume that f is constant on each equivalence classes here. Okay, so the equivalence classes here are sets here, right, which represent those equivalence classes. Okay, and f is assumed to be constant on each of those equivalence classes. Okay, we need this assumption. So it will be clear why we need this assumption in a while. So then, if this is the case, f induces a new map f bar from the quotient space to Y, defined by f bar at the equivalence class containing P in S is equal to simply f of P for all P in S, right? So whenever we have a continuous function from S to Y, we will be able to construct this new function out of this function f, as long as we have f to be constant on each equivalence class. Okay. So note that the definition here needs to be well defined, and it only will be well defined if f is constant on each equivalence class here. Why? Because if I choose two different points from each equivalence class, they are the same point here, right? And then if the function is not constant on that equivalence class, then f will have two values for the same point here, right? More than one values at the same point here, which will violate the definition of a function. So in order to have f bar to be well defined, we need this assumption that f is constant on each equivalence class here in this quotient space. Okay, good. So this is how we have this, this is how we have this new function induced from this old function f. Okay, so this construction can be understood from the following commutative diagram. Okay, so we have this topological space S, and here is this continuous function f from S to Y, where Y is another topological space. We have this canonical projection map pi from S to the quotient space S quotiented out by twiddle. Okay, this is the quotient space, and pi is the canonical projection map. And this is the induced function from S quotiented out by twiddle to Y, right? And we want this diagram to commute. That is, we want f to be equal to, so you can go from S to Y via two paths. One directly from S to Y, and the other one via this quotient space. Okay, and they should be the same according to the commutativity of this diagram. All right, so it means that f is equal to f bar composed with pi. Okay, and this commutativity of the diagram is a consequence of the definition that the consequence of this definition actually, because fp is equal to f bar composed with pi evaluated at p, and pi of p is nothing but the equivalence class where p belongs, right? Which is this very definition of the induced map. All right. So, okay, now we have our first proposition of today's lecture. Let me state the proposition and then I'll prove it. Proposition 1. The induced map S bar from the quotient space to the topological space Y is continuous if and only if the map f from S to Y is continuous. Okay, one side is immediate, this direction. Okay, Well, it means that we are given this function f bar to be continuous, and we have to prove that f is continuous, right? And we know that from the definition or the commutative of the last diagram, f is nothing but f bar composed with pi, and by assumption f bar is continuous, so we use pi because pi is the canonical projection map, and the composition of the continuous function is again a continuous function, which proves that f is continuous. Okay, now this direction. Suppose, so now we got to start with f being continuous, and we will prove that f bar is continuous. Okay, so suppose f from s to y is continuous. Let v be open in y. Okay, since f is continuous, we have pre-image of v under f, which is the same as this guy from this. You see that we can write it like this, right? Follows from elementary set theory. Okay, and note that be careful about these notations, because these stand for the pre-image notation. It doesn't mean that these guys are invertible functions. Okay, so you got to be careful about these notations, and which follow from set theory, elementary set theory. So the pre-image of v can be written in this way, and from the continuity of f, it follows that this is open in S. Here. Okay, so since this is open in S, from the definition of quotient topology, we see that this guy the inverse image of V under F bar is open in the quotient space. Okay, which follows from the definition of quotient topology. Okay, so now, what have we found? We found that given V open in Y, the pre-image of V under F bar, is open in the quotient space, which means that F bar from the quotient space to Y is continuous. QED. Okay, good. Now, identification of a subset to a point. So we can construct new topological spaces in this way. Okay. Identification of a subset to a point. Okay, so we start with the fact that A is a subspace of a topological space S. Okay, A is a subspace of a topological space S. So we define a relation twiddle on S. Define twiddle on S in the following way. Okay, by declaring X to be equivalent to S for all X in S. X is equivalent to X, which is nothing but the reflexivity of an equivalence relation, and and x is equivalent to y for all xy in the subspace A. Okay, so that you collapse all the points on the subspace to a single point in the quotient space. Okay, so it is immediate from this definition of twiddle that twiddle is an equivalence relation. You can check immediately that it is reflexive, symmetric, and transitive. Is an equivalence relation. So in this case, so using this definition, we say that the quotient space S modded out by twiddle is obtained from S by identifying A to a point by means of this process. Okay. So now we'll take a bit of time to get back to our discussion on topology and see what it means by compactness in the context of topology. Okay. All right. So let's start our discussion on compactness in topology. So we write it like this: an interlude. Back to topology. To have a clear understanding of what we are going to do with the construction of real projective space, we need these understandings. Okay. So compactness. Okay. So the story begins with a topological space as a topological space. Okay. Now we are going to define an open cover first. So a collection U alpha of open subsets is said to be an open cover of S if S is contained in the union of all these open sets. Okay. Now notice that since the open sets are in the topology of S, this is actually an equality. Why? Because all these open sets are contained in S, because we are talking about open sets in the topology of S. So their union will also be contained in S. So both these containments, with the help of these containments, we have this equality. Okay. Okay. Now, with the help of subspace topology, we can equip a subset A of a topological S with the property of a topological space, right? So say A is a subset of the topological space S. We can give A the subspace topology and make it a topological space by its own right. Okay. Now, this subspace A can be covered by open sets in A or by open sets in S. Okay. So there are two possible ways of covering A. One is by open sets in S, the other one by open sets in A. So we'll have two possibilities: an open cover of A in S, which is a collection of open sets in S that covers A. That is, from the definition of covering, A is contained in the union of these open sets. Okay, so it is important to note here that when we are talking about A being a subset of S, in particular if A is a proper subset of S, then this is a strict containment. Okay. Like in the previous case, we cannot put an equality here. Okay. Good. On the other hand, if you have an open cover, if you have an open cover of A, then A then it means that we have a collection of open sets in A in subspace topology, okay? Because A inherits the topology, from S, which is the subspace topology. In subspace topology, that covers A. Okay, and here we can write that A is contained in the union of all these open sets, and we can write it as an equality, like we discussed earlier, right? In this case, we can write an equality as each U alpha is contained in A, right? Okay. Now the definition of a compact topological space. A is compact if and only if every open cover of A in A, remember, in A, in the definition we have in A, has a finite subcover. So which means that in the cover there is a finite subcollection which also covers A. Okay. Alright, so let us try to have a look at some results, and then we'll have a better understanding what it means by this finite subcover. Okay. So we have our second proposition. A subspace A of a topological space is compact if and only if every open cover of A in in S. Okay, we can enlarge this to S. So in the definition we had in A, okay, remember, but so the result tells us that we can also take this cover in S. Okay, in S has a finite subcover. Proof. Okay. Let's see how the proof goes. So we are going to prove this direction first. Okay. Assume a compact. Okay. So this subspace A is compact. We have to prove that every open cover of A in S has a finite subcover. And so since we have to prove that every open cover of A in S has a finite subcover, we have to start with an open cover of A in S. So we assume that U alpha be an open cover of A in S. We have to show that there is a finite subcover of this cover. Then we are done. We are done with this direction. Okay, so let me draw a picture for you for this, intuitive approach. So this is our set A, subset A of some bigger topological space F, which is equipped with the subspace topology and hence is a subspace. And this is an open cover of A in S, not in A, in S. Okay. So this is a schematic diagram of an open cover of the subspace A in S. Okay. Now, so then, since this is an open cover of A in S, from the definition of open cover, we know that A is a subspace of, A is a subset. A is contained in this union, okay? And since A is contained in this union, of course, A is contained in the union intersected with A. And, again from elementary set theory, we see that this is nothing but the union of all these individual intersections. Okay. So we immediately see that A is contained in this union of open sets, right? Okay. These are the open sets in the subspace topology of A, right? And which means that this is an open cover of A in A, right? These are open sets in subspace topology of A, and this is a cover of A, since A is contained in the union of these open sets in A, and therefore this collection is an open cover of A in A. All right. And now, since A is compact by hypothesis, right? This cover has a finite subcover. Let us denote that finite subcover with U alpha I intersected with A from I equal to 1 to R. Okay. And by subcover we mean that A is contained in the union of these finitely many sets. I equal to 1 to R, U alpha I intersected with A. Good. And again, by elementary set theory, it can be written down as the union of this finitely many sets intersected with A. And this intersection is contained in this union. In other words, A is contained in this union. So we started with this open cover of A in S, and we have found a finite subcover of this cover. This is actually what we were looking for. Every open cover of A in S has a finite subcover. So we are done with this direction. Now for the other direction, suppose, so we are going to assume now that every open cover of A in S has a finite, subcover. Okay, so that's the assumption now, and we have to prove that A is compact. Okay, so in order for us to prove that A is compact, we have to use the definition of compactness that we have here. Okay, so we'll take an open cover of A in A, and then prove that open cover has a finite subcover. So we get started with V alpha being an open cover of A in A. Okay, because we are going to take the help of this definition. Now the goal is to prove that there is a finite cover, the finite subcover of this cover. Okay, then we'll be done proving that A is indeed compact. Okay, now since each V alpha is an open set in A by the definition of subspace topology, there is indeed an open set U alpha in S such that you can write V alpha as the intersection of that U alpha with A. Okay, so get back to the definition of subspace topology in the first lecture. You'll see that every open set in the subspace topology can be written down in this way. Okay, now since this is the case, from the definition of open cover, we know that A is contained in the union of all these open sets, which according to this equality reduces to this expression. And again, by elementary set theory, this is going to be this expression, and this is obviously contained in each of the constitutes of the intersection. So we have seen that A is contained in this union. which means that which means that U alpha is an open cover of A and S, right? Because these U alphas are open in S, right? Are open. So this collection is an open cover of A in S, remember. And by assumption, every open cover of A in S has a finite subcover, right? And there exists a finite subcover, which is this, okay, such that A is contained in this finite subcover, right? According to the assumption. So we have seen that if okay, since this holds, A is contained in this finite union of open sets, one has A being contained in this finite union intersected with A, right? Which is nothing but, again by elementary set theory, U sub alpha I intersected with A. And by the definition of V alphas, by the definition of U alphas to be more precise, this is nothing but the union of V alpha i's. Okay. So we have found that A is contained in this finite union. What does it mean? It means that V alpha I equal to R is a finite subcover of V alpha that covers A in A. Therefore, from the definition of compactness, A is compact. QED. Good. Okay, now I think I'll take a break now and get back to you with 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 some more results on compactness. Okay, thank you for attending the first segment.